Today's lecture is about normalization, so database normalization. What is normalization? Normalization is a very important step in database design. This step is done before you start implementing your database. So after you collect the data needed, the requirements for the application, what you do next is you do the AR diagram and then you try some data. You try some data on the AR diagram to see if they are working correctly. At this point, you're going to figure out some anomalies. These anomalies, these problems has to be addressed through normalization. So after the ER designing step, there should be a normalization step that is done before you implement your project. Alright, so what is normalization? So normalization is a process in which we examine relations for anomalies. So I want to detect any problems in your databases, any anomalies by splitting one table into more tables. Of course, we know that this is it's costly to have more tables, but if you have to and if there are anomalies, you should actually split your relation into more relations. So what you do with the first step, you create your ER diagram with the tables that you need, but if there are anomalies, then you will have to split the tables even more. And here in this session today, we will learn when do we have to do that and how. So second point here is saying that normalization is a very important part of the database development process. So the database designer start to get at this point the first look into how the data is going to interact in the database. And there you will find problems, okay, with the database structure that's going to cause, when we say problems, which means that it's going to cause me some data errors, some non-correct data or non-reliable data, so we have to avoid that. So we have to, as we know from before, we have to avoid allowing the entrance data entry of data that's not reliable, that's not correct. Okay, so to avoid this, the normalization is going to ensure that the data is going to be correct. So finding problems with the database structure is strongly preferred to finding problems along in the development process. So it's good to figure out the problems in the design, okay, before you get it after the development, and then you will have to get back to whatever code you have, whatever queries you had, and it's going to be very messy. That's why normalization is done at the design phase. As you see here, because at this point it's easy to fix and then go back to the ER diagram and fix it again, so it would be much easier at this step. So what we say, normalization will push you into maybe splitting your relations further in order to ensure the correctness of the data in the database. So we're saying here that normalization can also cause a trade-off. There's a trade-off between data redundancy and performance. Okay, so you either want to have data redundancy, you have a lot of data that's repeated, or you have to worry more about performance. So when you have more tables, okay, then this is gonna have some gonna cause the performance, okay. However, having more data would be easier. So normalizing a relation reduces data redundancy. It will reduce the redundancy, but it will introduce more joins and more tables, okay. So you will avoid the repeated data because you will have a separate table for, let's say, two attributes instead of having them repeated along the table. okay, there will be a separate table. For example, for location, and let's say city, okay, instead of having it repeated, location X, city Beirut, for example, having it repeated for every attribute in the employee table, we will have a separate location table, okay? And in this case, we have reduced the repetition, but we have introduced another table, okay, which is going to cause more joins. However, this is important, so we do it if it's important actually for the correctness of the database. So let's see all this introduction about normalization. Let's see how actually it's done. So let's recall the relation model, okay? Now we have relations, which are made up of attributes. Okay, so these are some points which you have already seen many times. The relation is a set of attributes with values for each attribute, such that each column value must be a single value only, not a double value, a single value. Each attribute is a single value. All values for a given column must be of the same type, so each attribute has a type. Each attribute should have a unique name in a relation, in one relation. The order of attributes is insignificant, which means that whether it's the first column or the last column, it's not of any importance. No two tuples, there's no two rows in a relation can be identical, so each row should be different from the other. And also the order of these rows is insignificant. So these points you already know, and you have already, they're innate to you by now. So when I talk about normalization, we have to define something called functional dependencies. So normalization is all about functional dependencies. There are going to be some values that depend on others, and those values I have to put them, or these attributes, I have to put them in separate table, and that's the basic idea of normalization that you will discover today. So what's a functional dependency? It describes a relationship between attributes within a single relation. So there are attributes in a relation, so within a relation. So all our normalization, okay, is done on single relations. Okay, so I have a relation, I have a table, and I find a problem in this table, and then I split it into more tables. So we're taking one relation at a time, and in function dependencies also we take one relation at a time. For example, so an attribute is functionally, so you figure out that one attribute depends on another attribute. So if you can use the value of one attribute to determine the value of another, this is called function dependency. So I'm going to say that the student major, okay, is, I can get the student major from student ID. So we say that student major depends on student ID. So we can determine student major from student ID. We can determine the grade of the student, okay, from the semester, course code, and student ID. So I need student ID, course number, and semester in order to get the grade. Okay, so these are some examples of dependencies. So the right-hand side depends, functionally dependent on the left-hand side, in that, what we mean by that is that the right-hand side, okay, can be determined only from the left-hand side. So we use the arrow symbol to indicate a function dependency. So x, okay, arrow y is read as x functionally determines y. So y is determined by x. The attributes that are on the left-hand side are called determinants. So they determine the other value, the value of the attribute on the right-hand side. So that the left-hand side attributes are called determinants. So when we get When we say determinants, this means, for example, in here A, and we read it as A determines B. So given a value of A, we can uniquely determine one value for B. So if I'm given student ID, I can definitely get his major. If I'm given student ID, course number, and semester, I can definitely get his grade. كمان a recall of another definition before we start in here with normalization. So keys and uniqueness. When I say key alone in this session, what I mean by key is primary key. And as we know from before, one or more attributes that uniquely identify a row in a relation is called a primary key, or as we refer it in this session, key. The selection of keys will depend on the particular application being considered, and you know this by now, okay? In most cases, the key for a relation, okay, is done in the ER diagram, in the ER model step. So it's about, we're saying here, it's up to the user in order to figure out which key is most appropriate to be the primary key. So no two relations should have exactly the same values, right? So we know that, okay, no two relations should have exactly the same values. Thus, a candidate key would consist of all the attributes in a relation. So if you cannot find what I'm saying here, could you just say I cannot find a primary key for this table? If you cannot find a primary key for a table, then all the attributes are a single key. We consider it primary key. This is a worst case scenario. So the worst case scenario is that all the attributes, okay, are underlined and they're all together form the primary key, because we know in a relation no two tuples, okay, are the same, so you're sure that they're different. Okay, so if you cannot find one attribute which is different in each row, then the whole row, from the definition of the databases, the whole row is different from the other row. And your attribute or your key would be all the attributes. So we're saying that for sure, okay, so for sure there's one function dependency, which is the key, okay, will define all the other attributes. What does this mean? So if you understand primary key very well, you would understand this function dependency very well. So what are we saying here? If I have a primary key, can I tell which row it is? The answer is yes. So if you have the primary key, then you can tell all the other attributes, right? So this is a functional dependency that's present in for all relations, that the primary key, and which is allowed. We are allowed to have this functional dependency, is allowed, okay? However, we will have a problem that not all determinants are keys, which means that we're going to have some attributes that are going to uniquely define other attributes, and those we want to have them removed and put in a separate table. This is again the idea of normalization. Let's look at some examples here. So what have we here? We have a relation called hourly employees. Have the SSN, name, lot, rating. So you have 1, 2, 3, 4, 5. You have 6 attributes, and the primary key or the key is the SSN. So we sometimes denote a relation by listing the attributes, or in this case, we listed the first letter of each attribute. So this is the set of the attributes. So let's look at some functional dependencies on hourly employees. So we're going to look for functional dependencies per relation. So normalization is done per relation. Function dependency per relation. What's the relation? Yeah, table hourly employees. So SSN is the key, then I'm sure that SSN or S, I named it here S, uniquely defines every tuple. Okay, all the other attributes. Why? Because S is the primary key, and from the primary key you can find the row. Okay, so how is it? How is this translated in function dependency? It's translated as determines all the other attributes in the row. But we have another dependency here, which is the rating. Okay, determines the wage per hour. So the rating his rating, the rating of the employee determines the wage that he gets per hour. And this is a functional dependency that we need to remove because it's going to cause a problem. Another functional dependency that's trivial dependency is that every attribute determines itself. Okay. So let's figure some problems due to, for example, R determines W. So how is this? So what problems are going to exist? Let's look at these examples. Okay. So as you can see, when the rate is 8, the wage is 10. Okay. When the rate is 5, the wage is 7. So the wage is uniquely determined by the rate. So why is this causing anomaly? Why is it causing problems? For example, if we update R or W, if we want to update a certain row, okay. So let's say we change W, okay. So we change the value of W. If W here, let's say, for example, becomes 11, yeah. Then this rule is this is not valid anymore. So if the rate is 8, which should be 10. However, when you update it, you only updated W, and this is allowed. So you are allowed to do something that breaks the application rule. In the application, R should uniquely define W, which means if the rate is 8, W should be 10. However, when you update it, you just updated W, and this is feasible because of the rules of the database. You can update any table. Attribute in a table, that's fine. Insertion anomaly also as well. What if we insert an employee, okay, and we don't know the hourly wage for the rating, okay? So what should the hourly rate be? So we know the rating, but we don't know the hourly rate. But what's W? Okay, so we can give it any value and it will not be valid. Deletion. For example, if we delete these two employees, okay, now I don't know what's the wage if the rate was 5. So there's information missing now. This information should exist even or persist even if these two employees are removed. However, okay, because they're the only employees that have 5 as the rating, okay, as the rate, and from which I can determine the wage. All right. So if you delete them, there's an information that should be there, but it's not valid anymore. It's not present anymore. So what is the solution? Typically, the solution is that we do RW. This RW as a table, a separate relation, and this is a relation with only R. So the result is that RW is put at a separate relation. Okay, so instead of, as we said before, instead of having it repeated for every 8, you have 10, 10. For every 5, you have 7, 7. We have reduced redundancy, but we have increased more. You will have the performance problem. It's not problem, but we have to do more joins, more tables. Okay, and this is going to affect the performance. So the solution is decomposing it into a separate relation, and we call this. We separate them. We split it vertically. Okay, vertically, which means that we split vertically, which means we create another relation. After this introduction and the explanation of these new terms, now it will be very easy to define the normalization process. Understanding all what we said so far will make it easy to understand the normalization process. So each relation can belong to a certain class of normal forms. So as I said, normalization is done per relation. So some relations can have a certain normal form. So normal forms are given names, such as we have normal form 1, second normal form, first normal form, third normal form, Boy's code normal form, fourth normal form, fifth normal form, domain key normal form. So these are the normal forms that we have. We're going to discuss some of them in this session. We say that these forms are cumulative in that a normal form that's in the third normal form is also second normal form and first normal form. If a relation is boy's code normal form, B, C, and F, then it's also third normal form, second normal form, and first normal form. So we say that they are cumulative. So what is the normalization process? So the normalization process for a given relation consists of, you first have to specify, so now we're doing the normalization process. How do we apply the normalization process? First step, you have to identify the key in a relation. Then you have to specify the functional dependencies. So what we're saying that if you have some tuples, some data, it will help you figure out the function dependencies you have in a relation. Apply the definition of each normal form and figure out whether it applies or not. So you figure out the definition of each normal form, starting with the first normal form. If a relation fails to meet the definition of a normal form, okay, you have to do some changing in the relation. For example, you split the relation into two new relations until it meets the definition. So this is the normalization process, like we discussed. Okay, so when you have function dependencies, you have to split it in order to figure out whether it's going to meet the new definition, the normal form definition. So what you do after you split it, then you retest the modified relations to ensure that they meet the definition of such a normal form, starting from the first normal form. So in the first normal form, how do I say that the relation is in the first normal form? If it meets the definition of a relation. Each attribute, first of all, so this is the definition of a relation. Okay, this is what we saw a minute in the beginning of the session. So first of all, it has to be a relation. So to be in first normal form, it has to be a relation. The second thing, if you have a key defined for the relation, then you can meet the unique row requirement, right? So if it's a relation and you have a key, okay, this means that you have satisfied unique key requirement, a unique row requirement of the relations on databases. So if it's a relation, okay, if it satisfies these 6 points, which are trivial, and if you have a key defined for a relation, primary key, then you are in the first normal form. So very easy. So you ensure that all your work is in the first normal form. For example, stocks is a relation. You have company, symbol, headquarters, date, close price. We're saying that symbol and date are the primary key. Okay? Why? Because they can uniquely define every row on the table. Simple as that. Now let's look at the second normal form. The second normal form, first of all, it has to be in the first normal form. So a relation is in the second normal form if all of its non-key attributes are dependent on all of the key. Another way to say that is that a relation is in second normal form if it is free from partial key dependencies. So we want the attributes to depend only on the primary key. No partial key dependencies are allowed. So they should depend. In this case, you have symbol and date. It's not allowed that an attribute depends on a single part, a partial key. Okay, a single part of the primary key. It should depend on the primary key together. Relations that have a single attribute for a key are automatically in the second normal form. So, as a conclusion, if a relation has a single key, primary key, then it's first normal form and second normal form. If it has double or triple or multiple key primary key, then we want to check if there are any partial dependencies key dependent. If there's an attribute that depends partially on a partial part of the key, then we have to fix that. Okay. So we're saying that this is one reason why we often use artificial identifiers, which means that if the table should have multiple key as a primary key, then what we do is we define an artificial identifier. We add just key here, we call it, let's say, ID, and it's an artificial identifier so that to avoid composite keys. So we'll add another key here. Okay, we define it to be the primary key. We give it unique value for each row. So for example, here we say that close price, okay, in this company database, stocks database, the close price is dependent on company and date. So the close price is dependent on company and date. So the following example relation is not in second normal form. We're saying that it's not in second normal form because close price depends on date and company, and this is not allowed. So let's see how we're going to see the partial dependency and how we're going to actually fix that. So to normalize it to the second normal form, so first of all, why am I normalizing to the second normal form? Because we have composite key. So what do? We first list the function dependencies. So we're saying that symbol by itself determines company and headquarters. We say also that symbol and date together, which is okay, because symbol and date are the primary key. Define company, headquarters, and close price. So we're saying here, consider that symbol date defines or determines close price. So we might use symbol date as our key, and that's what we did. Okay. However, so why did we choose it to be symbol date? Again, given that it was not given, saying that it was not given that this is the primary key. Figuring out that all the attributes are defined from symbol and date, then I can put symbol and date to be our key. However, we figured out that symbol alone, okay, is determining the headquarters. So this is a problem. This is a partial key. This is a partial key. Symbol alone, as you can see in this function dependency, symbol is defining company and symbol is determining headquarters. So this is a problem, but this is a partial key. This violates the rule for the second normal form in that part of our key determines a non-key attribute. Another name for this is partial key dependency. Why? Because symbol is a part of the key, yet it's defining one of the attributes, which is headquarters. What is the solution? As we said before, the solution is to divide it, to split it vertically. So we're going to have two relations. So since symbol defines company and headquarters, so why don't we put a table that contains symbol, company, and headquarters, and another table that contains symbol, date, and close price. So that's what we actually did. We divided them into two tables, okay, and from the symbol here of each tuple here, the symbol, from the symbol I can get the company and headquarters. So I have all the information there. However, it's split into two tables. So the original stocks table, okay, is now removed, and instead of the stocks, we have two tables or two relations that are company and stock price. Now some sample data and new function dependencies are over here, which is fine, okay? And now this is in the second normal form, because in the first place the primary key is one key, and this one is also in the second normal form, because close price is defined by symbol and date. And there are no partial dependencies. So for now, first normal form, second normal form. Now let's look at the third normal form. A relation is in the third normal form if it is in the second normal form, and in addition to that, it contains no transitive dependencies. What do we mean by transitive dependencies? Consider a relation R, okay, let's say on A, B, and C. If A determines B and B determines C, then A determines C. This is called transitive dependency, okay, three attributes with the above dependencies. So a transitive dependency is between three attributes, looks like this. A determines B, B determines C, and then A would determine C. For example, course code determines course number and section. So course code determines course number and section. Course number and section determines classroom and professor, and therefore course code determines classroom and professor. This is an example of transient dependencies. Okay, let's look at another example here. In the second normal form, we have company, symbol, and headquarters. What functional dependencies can we see here? Symbol defines the company. When I say MSFT, that's definitely Microsoft. Microsoft's headquarters is in Redmond, so the company specifies headquarters. So therefore, symbol specifies headquarters. This is called a transitive dependency. So why is it important to remove this? To remove such dependency, because as we see, what happened if we remove Oracle? Okay, there are two different facts that are going to be removed with it. So we have to keep two different facts. So to do that, what we do is that we divide the table into two tables. Company symbol and company headquarters. And that now if I remove Oracle, I still have that the Oracle's headquarters is in Redwood Shores, for example. Okay? So this is the idea of normalization, and this is the third normal form. If you have transit dependencies, okay, in the way Oracle company here was, then you have to divide them, to have to split them into two relations. And now these relations are in the first, second, and third normal forms. And now if I remove Oracle, I can still know where the headquarters are. Now Boyce code normal form, BCNF, a relation is in BCNF if every determinant is a candidate key. we said that not all determinants are keys. The determinants that are keys, we call them candidate key. So eventually we select a single candidate key to be the key for the relation, right? So if a key can determine other key and it's not a candidate key, then we are not in Boy's code normalization. So we should avoid keys that determine other keys. For example, let's look at the following example. We have fund ID, funds relation, we have fund ID, investment type, and manager. Funds consist of one or more investment types. You can have, for one fund, different investment. Funds are managed by one or more managers. Okay. Investment types can have one or more managers as well. So for example, common stock is managed by Smith and common stock is managed by Green. Managers only manage one type of investment. So while one type of investment can have different managers, common stock can be managed by Smith, common stock can be managed by Green, common stock can be managed by Smith again. But Smith can only manage common stock. So you cannot see Smith other than in common stock. So Smith can manage one type of investment. Understanding this, you can conclude the function dependencies. So once you understand the requirements of your database, then it's easy to define the different function dependencies that are present in the database. So we conclude that the fund ID and the investment type together define the manager. So if I know the investment type, common stock, can I tell the manager? If I know that it's common stock, can I say that's definitely Smith? No, because common stock could be Green. But if I know the fund ID and common stock, then I'm sure that the manager is Smith. The second functional dependency is saying that figuring out the fund ID and the manager. Okay, if the fund ID is 99 and Smith is the manager, so I'm sure that the investment type is common stock. Why? Because the manager determines the investment type. Okay, so if I know the manager, I definitely know what the investment type is because Smith only manages common stock. But if I know common stock, I cannot know manager, right? Because common stock could also have Green as manager. So these are the functional dependencies that we have. What problem do we have? So what problems do we have is that who is going to be the primary key, who is going to be the candidate key, and we figure out the manager, okay, is uniquely, the manager is uniquely determining the investment type, and that's going to be the problem. Let's see what we discussed here. So the combination of fund ID and investment type form a candidate key. Why? Fund ID and investment type, okay, because they define the other key, which is manager. Form a candidate key because you can use fund ID and investment type to uniquely identify a tuple in the relation. Similarly, the combination of fund ID and manager also forms a candidate key because we can use fund ID manager to uniquely identify a tuple. But I have a problem. Manager by itself is not a candidate key because you cannot use manager alone to uniquely identify a tuple in the relation. So these are candidate keys and they're okay, but manager is not a candidate key. However, Investment depends uniquely on manager, so we have to remove that. So first of all, we ask, is this funds first, second, and third normal form? Okay. Uh, First, what we have to do is figure out which is the key. So if we pick fund ID and investment type as the primary key, then okay, we have finished first normal form because we have a primary key. Now all the non-key attributes depend on all of the key because manager by itself, because all the other attributes are only manager, and manager depends on both fund ID and investment type together, then we're sure then that we are in the second normal form. No partial key dependencies. Are we in third normal form? Yes, we are, because there are no transitive dependencies. However, what could happen if we delete tuple with fund ID to 22? We will lose the fact that Brown manages the investment type growth stocks. So this is an information that we will lose. Okay. Why? Because investment type, because manager alone determines the investment type, and this is the relation that we should split. So therefore, while funds rejection is in first, second, and third normal form, it's not in BCNF because not all determinants are candidate key, because I could tell growth stocks from the manager only, and if I remove fund ID 22, I will not know anymore that Brown is a person, is a manager who manages growth stocks. There's an information now that's going to be missing in my database. That's why if we remove this, we should keep the information that Brown usually manages growth stocks. So to normalize it, so what did we do? We list all of the determinants, see if each determinant can act as a candidate key. For any determinant that is not a candidate key, and that was the case in manager, because manager was a determinant because it uniquely defines investment type, and it cannot be a primary key because it cannot uniquely define each row. We have to create a new relation, okay, to retain the determinant original form. So for our example, the determinants are the following, okay. So we said before, so this is like doing what we said, but in a more organized way. So these are the determinants of the fundamental, the function dependencies. We're saying that these can be candidate key, this can be candidate key, but manager cannot be candidate key. So what we do, we create a new relation that contains manager investment type, and another one that contains fund managers, that contains fund ID and managers. Okay. So if we remove fund 22 here, we can still know that, I don't know what was Brown, okay, this manager invests that type of investment. We didn't lose it because it's already present in this, we didn't lose that information because it's already present in this table. So we say that we have retained the determinant manager in the original relation managers. And again, after you do that, so usually you have a big database, you should again check each new relation, okay, whether they meet the definitions of the first, second, third, and BCNF normal forms. Another normal form is the fourth normal form. A relation is in the fourth normal form if it is in the BCNF normal form and it contains no multi-valued dependencies. What do you mean by multi-valued dependency? It's a type of function dependency where the determinant can determine more than one value. So more formally, there are three criteria. The first thing, that in this relation there should be at least three attributes. the relation that I'm checking for fourth normal form, there has to be 3 attributes. Let's say they're called A, B, and C. Given A, one can determine multiple values of B. And given A, one can also determine multiple values of C. And therefore, B and C are independent of, and B and C are independent of one another. So if you have this scenario, then you have multi-value dependency, and you have to avoid it. How do I avoid? Do I avoid it by also splitting the relation logically? For example, here, student ID. So what do we have here? Student ID, major activities, student ID. A student can be in more than one major, and he can be in more than one activity. Okay. And you have this, so that's why you have these functional dependencies. That student ID determines several majors, and student ID determines multiple activities. So in this case, you have some data that's redundant, and that's going to cause me some problems. Okay. So what I did here is for CIS, I put baseball and volleyball, and for accounting, I put baseball and volleyball. And this repetition should be avoided. Another example of multi-value dependencies is this relation over here. We don't have regular functional dependencies. We have only multi-valued dependencies, okay, where the portfolio ID determines multiple stock funds, as you can see, and portfolio ID determines multiple bond funds. And see how we had to repeat some data in order to put all the information. And stock fund and bond fund are independent of each other. So you can have this stock fund and this bond fund or this bond fund, and you have to put all this information here to show that these two funds or these two attributes are independent. Or you can say that if you want to add a stock fund without adding a bond fund, then you have to put it as a null here. Okay, and that's the problem that we want to actually remove. So to remove this redundancy and to preserve the information, all the information that we need, what we do is that we split the table into 2 tables, one for bond fund and one for stock fund. Or in the example before of tables of the student ID, okay, student table, we can have 2 tables, one for major and one for activity. Now these are in the fourth normal form. And as I said, whenever a table is fixed to, or a relation is fixed to have a certain normal form, you have to also recheck the resulting relations, whether they're also if they also are in that normal form. In this example, we have reached to fourth normal form. And that's where I'm going to stop. And with this, you have actually gained the sufficient information and practice for the database course.